In this video tutorial, we will look how to design a neuron core arithmetic data path. So we're going to use all of our design that we have designed in previous lab and this lab. For example, we're going to use multiplication that we designed in this lab, and then we're going to use the addition that we have designed in the previous lab. So for example, in this neuron core, it is a combinational design. So the axiom, for example, n, it is 3, and q, it is 2. So the axons, they are of 3 bits. So all the axons are 3 bit. So we have 2 axons and 2 synapses, which are 2 bit, and the synapse is 2 bit here too. So when we do multiplication of the axon and synapse, we will have a product. For example, here we're going to have product 1 and product 2, and this product are of 5 bit. So the product here, it's 5 bit. The answer of the product is 5 bit. So we will have product 1 and product 2, and then we will sum product 1 and product 2 using our previous, this we're going to use RCA, our ripple carry adder, to sum it. And the answer of this, it should be of 6 bit. Because if we take the worst case scenario here of 5 bit, so it is 5 bit, it is 16. For example, 16 plus 16, this is 32, which is of the 5 bit. So it's 2.5, which is 16, is 32. So we can see that we can represent the final answer in the 6 bit. The length of this one is 6 bit, which is sum. And then the summation of it, we're going to divide by 3 bit. So 2 to 3, so which is 3 bit. So the answer of this, of y, the final answer, it is of 3 bit. So this one is a combinational design, and then we're going to design this into a Verilog file. So let's design this neuron core into a Verilog file. So what we need to do now, it is to create a new Verilog file. And then we can name this, we can save this Verilog file as neuron core. So we need to design our model here, model name. So we're going to name it neuron core. And then end module. For example, if we look at our design here, we can see that the inputs are the 2 axon, 2 synapse, those are inputs, and we have an output, which is the y, and then we have internal wires, product 1 and product 2, and sum. Axon 1, axon 2, synapse 1, which is W1, and W2, and Y. It is the output. And then we need to declare those. So input so this is input of x1 and x2, which they are of 3-bit, and then input of the synapse, which is WV, it is of 2 bits. So it is W1 and W2. And then we have our output, which is Y, and that it is 3-bit. And then we have our internal wires, which are this one, product 1 and product 2, and sum. So we can write internal wires, product 1 and product 2, and those are of 5-bit. So those are 5 bits. And then now we need to instantiate our multiplication, addition, and division. So let us open those files. For example, let's open multiplication, and let's open the divisions. And then we need addition, so we need to open our add sub ripple carrier adder. So first we're gonna do multiplication, so we need to insert this multiplication. So it was MQ multi, this one MQ multi, and then we have MQP. So M, it was X, so X, for example, X1. What I'm doing now here, it is this one. I'm doing this, the first multiplication, this one. So it is M, which is X1, Q, it is the synapse, which is W1, and the answer P, it is product 1, this one. And then we need to close this and give it a module name, so we can call it M1. Okay, we can just copy this one, give it a module 2. Now it is X2, W2, and the answer is on product 2. And then after we have done that, now we need to do the addition of product 1 and product 2. So we need to call instantiate our ripple carrier adder. So it is n bit RCA model 3 and we can look here, we have our carry in, X, Y, sum and carry out. So the first is carry in, and the carry in it is 0-bit. We don't have carry in, so we can just write it as 0-bit. and then the next position it is product 1, product 2, and then it is our sum. So we didn't declare our sum, and then our sum here, it is of 6-bit, but we can just use it as 5-bit because the answer of this one will be the 5-bit. So we can just write it here as S as sum, and then here we can write sum, and then we have a carry out, so we need to declare a carry out. So wire so we have a carry out here. So we know that in this ripple carry adder, since we know the sum it is of 6-bit, so this is 5-bit and the 6-bit is here. So here we need, okay, let me say it's not right, carry out should be carry out, yes. Then we need to close this one, and then we need to, because here our ripple carry adder it is 4-bit, but now this is 5-bit, so we need to make sure that we change the parameter of the ripple carry adder. So it is def param of module 3, and then we are looking after the parameter n that we want to change it, and then we can say that it is of 5-bit. Now what we're missing is the last one, the division here. So our division, it is this one here. So it is div by 2, so power of n, that is our model name, and then we give it module 4, and then we know from here our input is m and output is q, and our input, it should be this one here, the sum, which is 6-bit. So we can go here and then we can do the concatenation of the carry out and sum. So that is our m. This one is m, which is 6-bit, and the answer of it should be the output y, which is this one, output y of 3-bit. But we need to change def param of these two, the parameter, of the module 4, which is the, because here it is 4-bit, and then this one it need to be 3-bit. So def param dot n, and that it should be of 3-bit, because we are dividing here by 3 to the power of 3, which is 8. So now let's save it and set this as our top level and try to analyze and synthesize to see if we have done everything correctly. Okay, so we have successfully analyzed and synthesized. On the next video, we're gonna create a test bench file for this one and try to simulate it.